Hello, my name is Mike Heap from the University of Strasbourgh in France, and today I'll talk about how hydrothermal alteration can result in pore pressurization and volcano instability. The work I'll present today is part of a multidisciplinary and collaborative effort involving modelers, clay scientists, hydrogeophysicists, geotechnical engineers, and of course, volcanologists. The first question to ask is, why study volcano stability? Well, volcanoes are haphazardly built structures constructed from the products of both effusive and explosive volcanism and endogenous growth. These structures are inherently unstable and mass wasting events are frequent. For example, collapses in the last 10,000 years have resulted in at least 20,000 fatalities. One factor considered to encourage instability is hydrothermal alteration. This is because hydrothermally altered rocks are frequently found within the deposits of partial flank collapses. The photograph shows a scar of a landslide at La Soufrière de Guadeloupe. As you can see from the image, the rocks forming the scar are white and yellow, the result of hydrothermal alteration. But what does alteration do to a rock? Well, very broadly speaking, alteration could be split into two categories. Dissolution type alteration that increases porosity and decreases the strength of the rock, and precipitation type alteration that decreases porosity and increases the strength of the rock. Although large-scale modelling has shown that hydrothermal alteration can result in instability, models have thus far used poorly constrained or even assumed mechanical property input parameters. There's simply not enough data. Further, conventional wisdom is that alteration reduces stability by decreasing the rock's strength. However, less is known as to how porosity-reducing alteration can influence volcano stability. To explore the influence of porosity-reducing alteration on volcano stability, we will travel to Chaos Crags, a dome complex in California. Chaos Crags is shown in the top image. Rock samples for laboratory testing were collected from the now exposed altered carapace of the dome that forms the collapse scar. These samples were chosen based on their visible differences in alteration. The sampling localities are shown in the bottom image. Here are photographs of cores prepared from the collected samples, together with their alteration assemblages. As we can see, although all samples contain cristobalite and hematite, samples CC4A and B also contain smectite and kaolinite. Here we consider samples CCC as a relatively unaltered end-member. Petrophysical properties of the samples were then measured in the laboratory. We first measured their porosity and permeability. The device used to measure permeability is shown in the diagram on the right. Finally, we measured their uniaxial compressive strength, a widely used metric for rock strength, using the device shown on the left. The mechanical data from these tests was also used to determine the Young's modulus of the rock samples. Here are the results. Young's modulus and strength as a function of porosity are shown on the left, where each symbol represents a separate measurement on a separate core sample. These data show that all of the rocks have a similar value of Young's modulus and strength, apart from block CC4A, the black triangles, which is considerably stiffer and considerably stronger than the others. The graph on the right shows permeability as a function of porosity. These data show that the stronger CC4A block is also up to 4 orders of magnitude less permeable than the relatively unaltered block CCC. So how can we explain these data? Well, if we look at the microstructure of sample CC4A, we can see that the pores and cracks within the rock are filled or partially filled with alteration minerals. We can therefore conclude that sample CC4A is stronger but less permeable as a result of mineral precipitation. Okay, so let's summarize the findings so far. We found here that alteration, when associated with mineral precipitation, can strengthen a rock and reduce its permeability. However, although an increase in strength may be welcome, a large decrease in the permeability could invite high pore fluid pressures within the volcano. So, Could zones of high pore fluid pressure within a volcano influence its stability? Let's now test this hypothesis. To test this hypothesis, we'll use Hydrothermal Modeling Code LMM, an open source software which models the non-linear viscoelastoplastic deformation of rocks. To perform the modeling, we need volcano cross-sections and also to decide on rock physical property input parameters for the model. Here are the volcano cross-sections. As you can see, they're very simple. We decided to model 4 scenarios: an intact scenario in which there is no alteration zone, and 3 scenarios in which the alteration zone, shown in yellow, is progressively larger. We next need to decide on the rock physical property input parameters for the model. We used upscaled rock physical properties for unaltered block CCC and altered block CC4A to represent the intact and altered zones in our volcano, respectively. Finally, guided by our measurements of permeability, we decided to double the pore fluid pressure within the altered zone. Here are the modeling results. The color represents the displacement, where blue represents low displacement and yellow represents high displacement. The arrows show the magnitude and direction of the displacement. The 4 models shown are the results of the 4 different scenarios in which the size of the alteration zone increases from top to bottom. As you can see by the colors and arrows, the displacement increases as we increase the size of the alteration zone. We observe a downwards movement of the high central portion of the volcano and a lateral spreading of the flanks. Importantly, volcano spreading, promoted here by the high pore pressure zones, is thought to initiate catastrophic flank collapse. To summarize, our study shows that pore pressurization promoted by hydrothermal alteration can encourage volcano spreading and partial flank collapse, as well as other associated hazards. We therefore conclude that alteration capable of decreasing porosity and increasing strength also promotes volcano instability, but by a different mechanism. As a result, hydrothermal alteration should be monitored at volcanoes worldwide. But not only. Our study suggests that not just the alteration, but the type of alteration is important to understand and monitor. The location of zones of porosity increasing and porosity decreasing alteration within the volcano likely depends on factors such as pressure, temperature, and the pH and composition of the hydrothermal fluids. Thanks for listening, and let me know if you have any questions.
Merry Christmas, you filthy animal!